Today, we're going to talk about one of the biggest, and I mean biggest, challenges facing AI right now. Its absolutely massive appetite for energy. But it turns out, some researchers may have found a solution, and they did it by looking at the most efficient computer we know, the human brain.
Seriously, you have to ask yourself this question. When we think about the next generation of AI, what is actually going to power it? Because, well, that's becoming a real problem. You see, AI is just getting incredibly power hungry. The huge language models and all the complex systems we're starting to rely on, they're pushing our data centers to the absolute limit, creating an energy demands that, let's be honest, is just not sustainable.
Okay, so let's get into the weeds here. The root of this problem actually goes back to the way we've been building computers for like the last 70 years. It's a fundamental design issue called the von Neumann architecture, and it's created this bottleneck that engineers call the memory wall. Think about it like this. Your computer's processor is a super fast chef, but its memory, that's a pantry way down the hall. So for every single thing the chef does, it has to stop cooking, sprint to the pantry, grab one ingredient, and sprint all the way back. This is the memory wall. It's not the actual computing that's burning all the energy. It's this constant, frantic shuffling of data back and forth, back and forth.
So if our current design is kind of flawed, what's the alternative? Well, it turns out Nietzsche already built a much better one. Let's take a look at the ultimate model for efficient computing, the human brain. See, in the brain, the chef and the pantry are in the exact same place. The processing and the memory are woven together. Neurons and their connections, called synapses, they compute and store information all at once. And this is the whole idea behind a new field called neuromorphic computing, building computer chips that are actually structured like the brain.
So how do you get a piece of silicon to act like a neuron? Well, researchers are basically copying this process called the leaky integrate fire model. A neuron just listens. It gathers signals, and its internal charge starts to build up, and when it finally hits a certain point, bam! It fires off its own signal. It's this beautiful event-driven system. It only uses energy when it actually has something important to say.
But, and this is a big but, here's the twist. Even our most advanced brain-inspired chips are still thousands of times less efficient than a real brain. And the reason for that comes down to the most basic, fundamental component in all of modern electronics. You know, the transistor. It's the building block for everything. But the standard one we use, called a FinFET, it's kind of like a faucet that never quite turns all the way off. Even when it's supposed to be off, a tiny little bit of current is always dripping through. Now, multiply that little drip by the billions of transistors on a single chip, and you've got a massive waste of power. This is where our story gets really good. A team from UC Santa Barbara and Intel Labs came in with a breakthrough. They realized that to build a better brain, they needed a totally new building block, one that was, completely watertight.
And this slide really shows you the genius of their trade-off. On the left, you've got your standard FinFET. Yeah, it's fast, but it's leaky and it's a power hog. On the right, that's their new design, a 2D tunnel FET, or TFET. Now, it's a bit slower, sure, but it is incredibly low power, and it's virtually leak-proof. And it turns out, for building a computer that thinks like a brain, that's exactly what you want.
This chart right here really explains why that trade-off is just so brilliant. For normal computing, which runs super fast, the main energy cost is from constantly switching things on and off. But for neuromorphic computing, which is much slower and more sporadic, like a brain, the real killer is that static power, the energy that's just wasted by leakage. The TFET design attacks that static power waste head-on.
So the theory was solid, but the team didn't stop there. They went ahead and actually simulated a full digital neuron circuit, once with the standard leaky transistors and once with their new ultra-efficient ones, just to see what the real-world difference would be. And this is the big question, right? After going back to the drawing board and redesigning the most fundamental piece of computing to mimic the brain, how much energy did they actually end up saving? Well, the results are just staggering. Look at this graph. The green line way up at the top, that's the energy used by the standard circuit. And the blue line way down at the bottom, that's the new TFET circuit. For the kind of brain-like tasks we're talking about, the difference isn't just a little bit better, it's orders of magnitude better. Let's just put a number on it. 83 times more energy efficient. That's not a 10 or 20% improvement. That is a monumental leap forward. They're tackling the energy crisis at its absolute most fundamental level.
So what we're looking at here isn't just one cool new chip. No, this points to a completely different way we might design all computers in the future, moving away from the brute force model that we use today.
So, what does an 83 times efficiency gain actually mean for you and me? Well, it means having powerful, complex AI that can run right on your phone or on tiny little sensors without needing to phone home to the cloud. It means data centers that sip a tiny fraction of the energy they guzzle today. And ultimately, it could let us build even larger, more capable AI models that are truly inspired by the elegance of biology.
This whole thing leaves us with a really fascinating question to chew on. As we start to solve these deep, fundamental energy problems, are we getting closer to a world where our computers stop acting like super-fast calculators and start acting more like what they're trying to imitate? The powerful, elegant, and incredibly efficient human brain.